Hello, everyone. Thanks for joining us for today's Rockin pop-up. We are very excited to have received many submitted questions this week, so we want to make sure that we are able to have enough time to get to your questions. If you have any questions that come up during the course of the program, feel free to add them to the comments. But without further ado, we are going to be talking about how our beaches are born, how our landforms are formed, I'm going to pass it over to the geology gents, Gavin and Graham.
Hey, Marisa. That's exactly right. We're going to be looking at coastal landforms and how the lands are formed.
Graham, how the lands are formed. And this is going to be a really good one because it's close to home. It's always fun talking about Santa Cruz geology. And I think that we've got a bunch of really cool features. So let's jump into them.
Great. So yeah, we're used to these steep cliffs and beautiful sand beaches. But before we start looking at those cliffs and beaches, let's get ourselves in the mindset of moving sediment around and start looking at how these coastal areas start forming on a really small scale. So Gavin, you can't get much smaller than forming ripples along a coastline or in any sort of water environment. So Gavin, tell me how ripples are forming.
Yeah, totally, Graham, totally. So this is a really good place to start because the mindset that the audience should be thinking about is that all of Santa Cruz geology, or most of it, is sedimentary geology. It's built of sediments, and the way it moves around is the way the sediments are moving around. And so these ripples are a sedimentary feature. And it's also cool because they happen on very different scales. So the ripples that folks are probably used to seeing are the ones that happen on the beach. But ripples can also be so big you could see them from space. And so what they are these little waveforms that happen usually near the ground. Yep. And they happen when you have energy moving in back and forth in the same direction, only back and forth. So you might think of waves. That's waves and oceans and waters on the coasts often form these ripple waveforms, but also wind does the same thing. And so the waveforms we see on the beach, those are from the tides in the oceans, but the waveforms you might see in like the desert are oftentimes from wind. And so there are both these sort of shapes can be analogous to how they're forming.
That's right. Yeah. And so sometimes when you've got the back and forth motion of the waves, that helps keep really even slopes on either side. That's what gets us these wave ripples that I'm sure many of us have seen if we've ever gone, splashing in the water just off the coast. And then when we start getting into things like rivers or, places where we've got flowing water or flowing wind, that's where we start getting these we call them asymmetrical, but it's because they've got, gradual slopes on one side and then steep on another. And so we'll often see those in rivers, but we actually see them also often formed from wind. And this is what we often call sand dunes. And Gavin, we need to look no further than just a little bit down the coast to see some really world-class sand dunes, right?
Yeah, Graham, definitely. And these sorts of features are cool because they give you an idea, well, ripples do at least, of the paleo shorelines and the way that the waves were hitting paleo shores. So oftentimes you see ripples in the rock record and you could tell something about the environment. And so that does bring us to sand dunes. I didn't mean to backtrack.
Oh, no worries.
But we're in a great spot for sand dunes because what you need to make sand dunes is a bunch of sediment. We obviously have a lot of that with all the coastal erosion and the rivers leading to the coasts here. And also a lot of winds. And we know just going down to the beach on a windy day that we have strong enough winds that you could pick up all of the sediment on the coasts that we have and deposit them closer to land. And that's exactly what the dunes rather are. And so I'm sure that a lot of the audience has driven down to Monterey. And so you could see these pretty large sand dunes right offshore. And so they're right in our backyard, Graham.
Yeah, that's right. And so, you can also think about these things as sand dunes. They're not forming exactly the same as ripples. So I don't want to say they're the same thing as ripples, But one thing that's kind of cool about them is because sand dunes are much larger, you can actually see, like in this picture from the Sahara, where you've got ripples forming from the wind on top of dunes forming from the wind. So it's kind of cool to see these two different processes happening one on top of the other. And then we don't see that so much in Monterey these days because a lot of plants have had time to grow over and take over the top of these sand dunes, which has helped to keep them from migrating too much. But anyone who, you know, drives down Route 1 into Monterey has probably seen plenty of sand slumped down onto the roadway there. And that just goes to show that these sand dunes are active, right? These are active sedimentary features, and they're moving as the wind continues to move sand. But Gavin, we must say that there is something acting on these sand dunes today that is even more, you know, more intense than the action of wind on it. And what's happening there?
Well, Graham, the thing that happens in all of geology over time, erosion. And so to make these dunes, you need a pretty specific set of circumstances. You need a lot of available sediment. You need enough wind to be able to carry that sediment, and as the wind loses energy, it deposits its sediment on the dunes and they build up. Oftentimes, as you said, sand dunes can move. I grew up around things called the walking dunes because the dunes over time would actually move themselves as the wind picked up sediment on the lee side, on the shallow side, and dropped it on the steeper side. That happens all the time, but as time goes on and the environment changes, that those processes sometimes stop or slow, and that's when erosion takes over. And so that's what you're seeing in the Monterey sand dunes as you were referring to.
Yeah, that's right. And the reason we see them really having a tough time now when it comes to wave action, right? They're sort of eating away into these sand dunes, the waves are, and that's because the sea level has risen here from the time when these sand dunes were really forming. So when we look at our map of Monterey Bay, we see that where the coastline is now, there's this big stretch of pretty flat continental shelf. It's basically where, you know, the continent slopes out very, very gradually going out to sea. And so 20,000 years ago, during the last ice age, sea levels were a lot lower than they are now because so much water was stored up in ice caps that you had these really broad, open, really dry, sandy, you know, plains out there that had these these same strong onshore winds like we have today, but were blowing this sand up into what is, you know, the land of today's Monterey Bay and making these sand dunes. But as sea levels have risen since the end of the last ice age, they've started then chewing into these sand dunes and really, you know, really flattening them back out again as you know, sea levels have risen and will likely continue to rise.
If I may interject here, one of our questions that we did get this week was about the formation of the Monterey Bay, and it sounds like you're saying that one of the reasons why the Monterey Bay looks like it does today partially has to do with sea level rise, but could you guys also just touch on like why the Monterey Bay is there at all?
That's a really, really good question. I really like it. I see the Monterey Bay as an erosional feature. And so we've often referred to the faults that are running through this area of the world. We showed the San Gregorio Fault and the San Andreas Fault, and those are kind of running at sort of parallel to each other on the coast. Graham, did we show that slide yet?
We haven't, but we can give a sneak preview right down here.
So this area of the world has a bunch of faults, and so that right there kind of crunches up the rock, makes the rock a lot less durable to erosion. And another thing that happens is that as faults move, they put more competent rocks next to less competent rocks. So Monterey Bay is basically the result of having an area with less competent rocks. So the coastline erodes easier into this area. And it kind of starts this positive feedback loop. The rocks in Monterey Bay are easier to erode. They're more faulted, so you start getting erosion there. And then I'm sure that folks who live around here notice that there are a bunch of rivers that are cutting their way into the shoreline. And we see that with the Monterey Canyon. You have paleo rivers cutting the canyon, and underwater channels exacerbating those features. And so it's just a feedback between the erosion that's happening because of all these processes happening in this one area. You have anything to add to that, Graham?
No, Gavin, I think that really just about sums it up. What you've got going on in here is you can see these mountains rising up here just from looking at this map, right? We see the Santa Cruz Mountains right in our backyard, and Big Sur just down across the bay from us. And so you've got these places where you're driving strong, you're building rock up, you're lifting it up, and having these really strong sort of ramparts on either end of the bay. And that's, helping to channel waves and winds into this area that just doesn't have that same sort of support going into it. And so these end up turning into these drainages that sort of sweep into this area. And whether you bring sea level up or you lower it down, this is always kind of an area that's going to be a little bit softer and more sedimentary, and then just becomes really conducive to being this lower lying area that turns into a bay.
Like there's these less erosive rocks on both sides of it. There's more erosive kind of area, maybe because of some rivers. So it's just like all of the energy is getting like funneled into one spot, which is causing this bay to form. And is that also why there's the canyon out there as well? Or is the canyon just another factor in why that those energies are being funneled that way?
Yeah. Go ahead, Gavin.
I would say that the canyon is sort of just part of the erosion story. And I would add to this too, that what we were describing is sort of how you start the bay, but the bay is also, the shape of the bay is also changing over time. So you didn't start the bay as this sort of like mushroom rounded shape. What happens is you probably started the bay more of like a V shape, or which is how you usually start sort of erosive features, because they're usually river driven. But as you have these points on either side, and when you have wave action coming in and hitting these points, the way that they dissipate their energy wants to wrap around, and it doesn't hit exactly straight on. And so that sort of wave action and where the waves are dissipating is what's giving you this these sort of rounded shapes on the edges as well.
And an example of that is something that I think everyone watching is probably familiar with, which is natural bridges, right? The natural arches. So that's how that cave underneath the arch, this like, peninsula that's jutting out, is because of that energy that you're talking about, where the energy of the waves hitting this strong rock gets transported to the center of that. And
that's exactly right. How the wave energy is dissipating. Yep. Same idea.
Awesome. Okay. Well, thanks for that, guys.
Yeah. All right. So we've got some sand dunes, we've got ripples, we've got a great big bay forming. And of course, we'd miss coastal features altogether if we didn't take a moment to talk about beaches. So Gavin, this is, I think, a great question that we've been asked before, that I remember the first time I learned it. It really was awesome for me. But I think the best place to start when we understand beaches is we ask, where does the sand come from? So where does beach sand come from, Gavin?
Well, that's a great question, Graham. And it seems like it should have an easy answer, but there is some detail to it. Because as you know, if you go to the cliff edges in Santa Cruz or up one, not all of the edges have beaches. So it can't just simply be the erosion of the sides of the cliff. Most beach sand is actually transported from somewhere else. And so this is, again, the idea of where wave energy is dissipated. So I like this picture you have here, Graham. Can you take us through what's going on there?
Yeah. So when we've got winds blowing waves onto shores, those waves are almost never going to hit the shore like square on, right? There's always going to be a little bit of a slant to them. And that slant ends up sort of continually pushing things up along the current, up across the shore, and it results in what we call a longshore current. So even though waves are mostly hitting the shore head on, because they have a little slant, they end up pushing things down along the shore. And so here in like along the California Central Coast, we have longshore currents that are tending to drive things southward. And so what happens is when we get these little places that shelter around, you know, any great big point, that's a place that sort of breaks up that longshore current or slows it down or slows down that wave energy, and we start to collect sand. And Gavin, when you start to collect sand,
voila, you have beaches, Graham. It's
that's
all
right.
about where the wave energy starts to die and slow down, and it drops all of the sediments that it's holding. And so the thing I really, or the example of this I really like is the picture you have in the bottom right here, Graham.
Mm-hmm.
And so that is a picture, I think it was the 2017 winter that was the really, really rainy one. And I'm sure that a lot of folks are familiar with what happened at Cowell's Beach. You build up a big sandbar. And so what's happening there is exactly what we're describing. Up the shore to the north, you have these longshore currents. And because it was such a rainy winter, there was a lot more sediment coming out of those rivers up north. And those longshore currents would pick up all that sediment, and they would just keep carrying it until they found a place that they could drop it. And the place that they dropped it was Cowell's Beach, because they'd wrap around the point there, and they would lose energy when they turn around that point, and the energy would dissipate. And so that's why you have that sandbar. And I'm sure if we had 20 years worth of rainy winters like that, you'd build up Cowell's Beach pretty big. That's the beginning of a beach.
Oh, that's so cool. And it's always so remarkable just how quickly that can happen in the course of a season. You're building up almost a beach worth of sand. I'm always really, really impressed by how oceans work like that. So,
right. And I'm sure that, people installing jetties in a decade could have a big beach from a jetty. So
right. Yeah. And you can even see that down over here by the harbor where that big jetty has been built, and you've built out this great big patch of sand out in front of it just from it slowing down and stopping that longshore current.
Pretty interesting.
Yeah. Great. So we've got beaches, we've got ripples and dunes. And so now we must talk about how these sea cliffs are forming with these Wavecut platforms. Gavin, could you take us through the formation of a Wavecut platform?
Sure, Graham. Yeah. So you basically take high topographic rock. And when I mean topographic, I mean this rock is tens of meters above sea level. And it's probably like that because of the uplift. Remember, we talked about the faults in Santa Cruz. So you're uplifting the rocks there. And as those rocks uplift, the erosion of waves crashing into them every day, pretty much all the time, causes them to erode out. And so Santa Cruz is a great place to watch, ocean-driven erosion. There's erosion happening every day on those cliffs. And so there's also a really nice juxtaposition, basically, of really competent rocks, the Santa Cruz mudstone, and less competent rocks, the Pyroclastic sandstone. And that's why you get these sort of flat-lying areas like the bottom right picture there. Graham, Can you take us through that?
Yeah. And so this is a case where you've got, the same process that would normally form a pretty, flat surface up against a cliff, getting a little help from geology itself. So down here, these slabs are the Santa Cruz mudstone, which is a really tough and hard rock compared to the softer Pyroclastic sandstone that's plopped up on top of it. And so it ends up sort of, the waves come through and they sort of scour off the surface and are knocking down the softer, weaker rocks down on top of it. And so it's actually taking advantage of these geologic planes, these flat surfaces of the rocks, and really just sweeping off the wimpier stuff on top of it. And so that helps us get set up with this, steep cliff a steep cliff face and a real flat wave cut platform. But Gavin, you were talking about this uplift. Has this uplift stopped at all in the last several million years?
No, Graham, it's pretty ongoing. I did kind of put the cart before the horse here, because we are going to talk about that on this slide.
Oh, no worries. I like that you set us up for it.
So what happens is, do we have one cliff over a long period of time? Well, no. We know that we have the marine terraces. And so what those marine terraces are stranded paleo cliff faces. So as we alluded to, and you can see in this bottom right figure, we have the San Andreas Fault going north, the San Gregorio going south, and it's pinching the land together. That is Monterey Bay and Santa Cruz. And as that land is pinched between those two faults, it's pushing up. It's getting higher and higher above sea level over the past, couple of million years. And as the land goes up, and something else is happening during that time, Graham, what else is happening as you're raising that land up?
That's right. Over the course of this time, we have also had cycles in Earth's climate, and those cycles of Earth's climate have built up ice sheets and melted them down. And so what's happening is, as you're slowly lifting this land up, you also have sea level going up and down on a much faster, on a much shorter time scale compared to this. So things are raising up out of the ground at a rate of something, maybe like a centimeter per year, or something in the neighborhood of that. And then you've got, sea level going up by, several tens of meters every, 100,000 years or so. So as the ocean is almost like breathing in a way, going up and down, eventually these cliffs will get lifted up and be just out of reach of the ocean. And what happens when what happens then, Gavin?
Well, Graham, we get some really steep roads in Santa Cruz, because those cliff edges are basically just stranded on the shore. And so in Santa Cruz, I think you could see 2 or 3 marine terraces, right, that are just stranded. So a really good place to see them is at the Long Marine Lab in the Seymour Center down by the coast there in the UCSC Coastal Campus. But really, if you go up any of the roads, Bay or Miramar, all of those steep roads are old marine terraces. Not something I love to bike up, though.
No, they do make it hard.
So what do you say, Graham? Did we do it? Is that the last of the
That's all we've got for our quick, tour through coastal landforms here in Santa Cruz. And I think marine terraces are a great way to, great place to stop at, because marine terraces are one of the most, Santa Cruz things for me. I've never lived somewhere else I've lived on the coast before, but never in a place with these, these steps of marine terraces that just go on and on up into the mountains.
They're really
pretty special thing.
Yeah. So
thanks for that. I have a further question about marine terraces, because I agree they are so interesting. And so it sounds like what you're saying is that there are these two processes at play. There's the uplift that's bringing these terraces up, but really it's because of the sea level rise and fall that's causing these big changes that are creating the larger sea cliffs. So I'm curious, if the sea level was staying the same, would you just have a more gradual slope going up then?
I think you would probably have something that's still maybe a little bit stepped, but it wouldn't be, you wouldn't quite have these, flat, and then big steep cliff, and then flat again. You would have something that I think would be a little bit more incremental, that's sort of capturing the changes in sea levels help to make these sea cliffs and their strandings be very punctuated.
Yeah.
Very
and then you were also speaking about the current Wavecut platforms that will be another terrace, presumably, down the line, or are considered terrace, and how those are formed partially because the Santa Cruz mudstone is so much more competent than the wimpy Pyroclastic formation that lies above it. And so do we see evidence of that with the terraces that have already been uplifted, where maybe the Santa Margarita sandstone was less competent or more competent than another formation? Do we see evidence of that when we go up the terraces?
That's a really good question. I don't know of any area that has evidence of that. Do you, Graham?
I don't either. No, I haven't heard of it. It certainly could be possible. And sometimes, there's only a few spots along the coast where you really see that taken advantage of, that contact between the Purissima and the Santa Cruz mudstone. So that tends to be, if we think about these marine terraces as something spanning, miles and miles, where you have that slight little juxtaposition there of those two units, that's only going over the course of maybe half a mile to a mile or so. So on the overall, what's really just going on here is this combination of erosion and uplift.
Yeah.
Right. And I also think that because the older stranded terraces are so, there's a lot of vegetation on them, there's been a lot of erosion, you'd probably erode off any sort of local phenomena like that, and you just get the large scale terrace that was the old sea cliff. You'd probably erode off any of those sort of features.
Right. Yeah. And even once you do get up to those older terraces that are higher up, it's often hard to even tell that they're a terrace because they're so eroded. It kind of just seems like a knoll.
That's right. They've got hundreds of thousands of years of rivers and soil creep and landslides that have made them almost unrecognizable.
Yeah. Cool. Well, I love talking about marine terraces. We may have an opportunity to talk about them next week too during our special 115th anniversary Rockin pop-up, where we go back through geologic history since the museum first opened our doors, which is exciting. But before we get there, we do have some more questions. We had a lot of questions come through this week, and we've already covered some of them. One of the questions, this person was interested in marine terraces, so we got that covered for her, but she was also interested in this very particular, very specific place on the East Coast. And so I sent you guys that question ahead of time so you could prepare for it, because I wasn't sure if you had heard of it before. So can you share with us a little bit about our brimstone question?
Yeah, I'd be glad to. So yeah, we received a question about a location or a brimstone in the Prince Edward Island area of the northeastern United States and southeastern Canada. Brimstone is an old term used to describe sulfur. So I was a little surprised to hear about this brimstone. I had never heard of it before. Gavin, I don't know if you had ever heard wind of this.
No, yeah, brimstone is sort of an old style word for rocks. That's not really thrown around, but there's this particular rock you found, right, Graham?
That's right. So we investigated a little bit, and and we found a Brimstone Head in Newfoundland. So this arrow here is pointing to where it is, and Brimstone Head in Newfoundland is this really neat promontory. And Gavin, you ended up finding out that there's a very interesting theory about Brimstone Head in terms of the old assumption that the Earth was flat. Isn't that right?
That's right. It's one of the corners of the flat Earth, right?
That's right.
What it said.
And fortunately, we don't have to worry about it being a corner, since we have hence figured out that the Earth is indeed a sphere or a spheroid. And so we don't have to worry about that. But this is really kind of a funky looking thing. No, it is not made of sulfur. It is just a name, Brimstone Head. But it's actually got a pretty neat history in that it is a volcanic deposit. We call it a pyroclastic deposit. Gavin, what in the green earth is a pyroclastic deposit?
Well, a pyroclastic, I like the term because you, Graham, could be the one to say, well, pyro means this, clastic means this, fire and rock. You always like to look at the roots of words, but it's basically where you have a large volcano spewing a bunch of lava onto the earth, and it's the remnants of all of that magmatism. Right, Graham? Would you say that's a good general?
That's a perfect way to describe it, Gavin. So over 400 million years ago, in this area, there was a great big volcano, and there were all these sediments. You know, this was a sort of a shallow sea area, and these volcanoes were just pumping. Let me tell you, they were erupting and throwing tons of hot rock all over the place. And so that's exactly what Brimstone Head is. It's this old volcanic deposit that was buried deep beneath a bunch of other things, and as that coastal area of Newfoundland got eroded away between coastal processes and actually glaciations over the ice ages, that big sort of dome of volcanic material really just stood up against the test of time and stands there today as a testament to those strong pyroclastic deposits.
Yeah, so I think the question mentioned something about it coming from elsewhere. That's actually not the case. This is right in place. It doesn't come from anywhere else. And there was also another area, Prince Edward Island, that was mentioned. Most of what the question did get right is that most of those areas are sedimentary rock, and so Prince Edward Island is sedimentary rock, and Brimstone Head is sort of a whole different thing, but it's happening in place just by normal geologic phenomena.
Yep, that's right. And so certainly Brimstone Head is a stark and stunning rock feature that really does look out of place. But sometimes just through the sheer benefit of erosion, we can have these really sort of unique rock forms that just sort of do rise out of the ground through time. And then one other question, the asker of this question wondered if perhaps some cosmologic event might have been involved in placing such a weird looking thing around, and speculated about could a supernova have played a role, but which is not an unreasonable question. But the thing about supernova is that they don't tend to create anything rock-like. Gavin, supernovas are so hot and so energetic. What do they actually end up producing rather than anything like a rock?
Well, supernovas are the driving force that tends to take the gas cloud and start to make it collapse and form rocky bodies. So you could think of a supernova as the event that started off the formation of our solar system, but this is a much more grand scale than the scale of, say, rocks on Earth, right, Graham?
That's right. And so the last time we had a really local supernova that could have, put any decent amount of material in place was when we jump-started the formation of our solar system. And it actually brought in a bunch of really great high-energy radioactive isotopes like aluminum-26, which we actually astronomers look for in the background of our galaxy to try and find places where new stars where supernovae are occurring and new stars are starting to form, because those supernovae become really important for jump-starting solar systems just like our own.
That's right. Yeah, so without getting too far into it, supernovas make elements.
That's right.
And the rocks on Earth are a bit different from that.
Wow. That was a doozy. We covered a lot of ground there. And as my dad always likes to say, pyroclastic flow would be the worst way to go. But thanks so much for looking into that for our museum friend who was curious. We had some other questions too, so I think we should just keep on going and make sure that the people get what they want. And so we had some really great, specific questions about some Santa Cruz features, which is today's the day to talk about it, because we're talking about our coastal landscapes. And so another question was from our friend Frank, and he's curious about chert, and how chert is common on North Coast beaches like Waddell Beach, but that he says you hardly ever see it in the beaches around Santa Cruz. Do you have any insight into why chert might deposit in places and not in others?
Yeah, so generally we could start off with why you're getting chert and why it happens in certain areas. So chert is formed when you have a bunch of little critters that isolate the element silica in their shells and they die, and they make these layers that are basically mud, but they're full of the element silica. We call them siliceous oozes in the geology community. And over time, they'll solidify and make chert. So Santa Cruz, great place to get chert. And actually, if you walk up and down the rocks in on, say, West Cliff, you can find little lenses of chert. But in terms of the big pieces, those sorts of things aren't really local to, you know, the west side of Santa Cruz, say. But Graham, you had an idea of why you might get them in the North Coast and why they might be sort of not here locally.
Yeah, yeah, and we've, you know, I would consider us both, you know, a pair of chert lovers. And so we always enjoy when folks, you know, will show up with some chert for the Rockin pop-ups, and we get to talk about that. I think there's some pretty, so there's no local coastal rock that has lots of chert in it, like you said, but there is more chert that's accumulated and has been uplifted into the Santa Cruz Mountains. And so that ends up making its way down to the coast by rivers. And in order for it to get to beaches, you need those long shore currents to be transporting it along. And so, you know, the distribution of chert across beaches in the greater, you know, Santa Cruz, Monterey Bay, and North Coast areas all has to do with how well that longshore current is doing in moving those materials down, down the coastline. And so just depending on the sort of overall wave climate, that will determine, you know, just how far they make it and what areas you end up concentrating it in.
Yeah, that's really interesting. I have heard some people posit at the museum that possibly like questioning whether or not when you find little bits of chert, say right by Seabright Beach, whether they could have been fragments of people working that stone, because we've had people living here for thousands of years, and where the museum is located is on UEP territory. And so, and we know that people have traded for that commodity and that resource for many, many years too. But it sounds to me like it's very, very likely that what we're seeing is little remnants that have made it just a little bit farther than most of them that are coming down from, I know there's a good population of chert from the Año Nuevo area, right? Which also has to do with faults of kind of what our original asker about the Brimstone question was wondering if something formed somewhere else and was brought there. That's kind of the story of our local chert too, right? That it was formed farther south and that it was brought up farther north.
Yes, yeah, definitely. Right. Yeah, it really depends on what kind of rocks you're sourcing. So if it turns out that the beaches up north they're probably closer to a larger chert lens, and that just has to do with where those rivers and longshore currents are sourcing rocks from. And also the erosion, right? You probably wouldn't see chert on a beach that only has like tiny sand due to a lot of like coastal erosion.
Right, totally. So another question from Frank has to do with the Opal Cliffs area, which I don't know if anyone watching is familiar with that, but kind of near like Pleasure Point, Capitola, in that area. And Frank he's noticed a phenomenon that puzzles him. So he specifically said that there's a modern Wavecut platform that has channels carved into it by the back and forth action of the waves and sand, and these channels are perpendicular to the wave crests. Similar channels occur on the nearby Pleistocene Wavecut platform, but they are oriented more to the southeast northwest, so they're oriented differently. Has anyone studied these as possible indicators of shoreline orientation during the late Pleistocene?
So I think the best way, yeah, so that's a really keen observation to sort of recognize like the directions of these channels. Channels are often, you know, representing a downhill slope where water's, you know, flowing in that direction, and water always wants to coalesce and find the easiest path down. So that's what we know channels are a good marker of. If I were going to make a bet about the shoreline orientation, I would look to the cliffs. And that's what those terraces are, right? Those are all the old backdrops of the shorelines. And so we actually have a pretty good sense just from finding these steep slopes, right, where these cliffs are, where our shorelines used to be. Although I must say I'm not familiar with these channels. I haven't put my nose to them, so to speak.
Yeah, that's right. But I am not positive as to which channels Frank's referring to either at Opal Cliffs. But yeah, as you said, there's a few things that will make a channel in the side of one of the coastal cliffs. You have your rivers, like you were saying, Graham. So those are, you have the cliff here, and the rivers are coming down off of the high topographic area. So those are going to be perpendicular to the shoreline. And also, oftentimes we get pocket beaches and little channelized areas on the coast that aren't necessarily right parallel to where the waves are cresting or where the waves are hitting. And that is a similar phenomena that we were talking about at other parts in this Rockin' pop-up, that where you dissipate wave energy oftentimes isn't exactly perpendicular to the cliff. So you're oftentimes dissipating wave energy around a point or something. And so it can make a channel or an area that the platform is cut into that's not necessarily where you would expect, but it just has to do with the nuances to the cliff line and how the waves are hitting it. So that'd be my guess. One of those two phenomena is how you get some interesting and maybe not so intuitive features.
I love that there's just so many questions to ask about our own little tiny community here. So many mysteries still. It's wonderful. And one last question, actually two last questions. One just came in the comments. So just really quickly, do you guys have any sense of if Morro Bay is at all similar to the Newfoundland example that we were talking about?
Morro Bay. I'm not familiar. Graham, are you?
I no. Whenever I get put on the spot for my California.
Yeah. I would think not, because you're talking about pyroclastic flow, and I'm not. I'll have to look into it too. But from what I know about Morro Bay, I'd be surprised. We'll have to look. And then, so our last question was about resources. So someone is really interested in getting further into geology and is very used to studying science. She's a biologist, but for some reason, like, geology is just kind of a doozy for her. So she's curious if you have any suggestions for books, documentaries, podcasts, resources that will really help her to sink her teeth into this stuff and really get a better sense of how to get started with geology, other than watching the many pop-ups that we have made, of course.
Yeah, that's a great question. And it's something, as a geologist and having studied geology for a while now, that I've often found some frustration in, because if you're trying to get into the fundamentals, the 101 of geology, there aren't too many resources that are specifically there so that folks without a background can pick up the fundamentals, right? So as far as podcasts, there's not much. There are, to my knowledge, no online courses that you can take that I've found. There are sort of specific levels of resources you can get. So for instance, if you want to learn more about your area, there are the roadside geology text, little paperback books that you can get just in any bookstore, that oftentimes are, say, the roadside geology of California, or even any state, and even some more specific places. And then if you're trying to understand like a specific national park or something like that, oftentimes the national parks have a lot of guides if you go there or just look it up online. And then the USGS you can scour the internet for USGS pages. They often have sort of publicly leaning pages on certain things. Graham, do you have anything to add to that?
Yeah, I think that's a really great comprehensive list. I want to piggyback on your, if you're interested in like a particular, park, like Yosemite or or pinnacles. A lot of time parks will have like special U.S. Geologic Survey publications, or there'll be a national publication through the park that's usually like a little, like, it almost looks like a magazine. It's pretty low budget production, but sometimes we'll have park geologists that produce a little synopsis of, or a summary of, the geology of the park. Those I would often look for in visitor centers. I know a lot of those are closed right now during the pandemic, but I bet if you were to sniff around, your favorite park's website, you might be able to come to a little bit of information there. And then one book that I found really useful, that is written for a non-specialist, but I even learned a lot from when I read it, was Assembling California by John McPhee. That's a really fun read, and it takes you on the sort of whirlwind history of both geologic history and the history of geology as a science in California. And you can learn some tidbits about specific places within the state. But that's a little bit, that's less, less like, sinking your teeth really into the geology.
Yeah, well, I agree with that. I read that book, and it really helped me to kind of get a better, bigger picture, so that I feel like I'm more set up. I have this foundation to be able to understand more, getting into the nitty gritty a little bit more. And just for me personally, that's something that I would recommend, is starting with things that are a little bit more accessible and a little bit more relatable. And so, like, for me, I love geology, and I would have a really hard time if you like picked me up and placed me somewhere else on Earth and understanding geology there. But I feel like I'm really getting a good handle of my local geology, thanks largely to Gavin and Graham, but also because I can like go up to these places and I can look a little bit closer, and much like Frank, was doing at Opal Cliffs, looking at a phenomenon and then questioning it. And I really think that that's a great way to deepen your understanding. So thanks for all the recommendations, guys. And we're really looking forward to next week's program, which is again going to be part of a lineup of events celebrating the museum's long history. And so tomorrow our members are invited to register for our collections close-up event, where we're going to be digging into the many homes that the museum has had over the past 115 years, as well as how we care for our collections. And then next week, Gavin and Graham are going to be hosting the Rockin pop-up about the geologic history of Santa Cruz over that 115-year time span. And then next Friday is our anniversary. It's our birthday. And so we're going to have a special event then too. So we hope that everyone who's been joining us for these pop-ups will also join us for these other events and help us celebrate our long history, as well as look forward to the future. So thanks for joining us, and we'll see you all next week.